Welcome to IS622, Big Data and Machine Learning for the CUNY MS in Data Analytics program. I'm your instructor, Professor Rowe, and I'll be teaching this course in the fall. Let's talk about why big data and machine learning are important. First, we need to understand what big data is. For our purposes, we'll consider big data to be any data set that's too large for main memory. Big data can also be any data set that's moving so quickly that you can't keep it all. The other half of this course is machine learning. And what exactly is machine learning? For our purposes, we'll think of machine learning as being either a set of mathematical transformations, learning algorithms, and statistical methods. When we combine the two, what we see is that we have machine learning applied to big data. And that's the substantive matter of this course. Ultimately, with big data, you need to change the way algorithms are performed in order to handle the larger data sets. We'll be exploring the methods and techniques necessary to work with big data, and then also how machine learning algorithms are modified and adjusted in order to handle these massive data sets. With the volume of data increasing these days, applications of big data and machine learning are diverse. These include product recommendations or movie recommendations that you can see on Amazon or Netflix. We can also see it in terms of social media and graph analysis and understanding the connections between people and the associated knowledge graphs. There are also a lot of applications in terms of civic hacking, where public data sets for government transparency has become more prevalent. There's also a number of applications in healthcare and biotechnology, particularly in genomics, where you have data sets in the terabytes that can only be processed using a distributed system such as Hadoop. By its nature, this course is multidisciplinary. We have elements of computer science in order to deal with big data, and this includes functional programming and also a bit of linear algebra to deal with representations of the big data. On the other hand, we also have machine learning. And we'll see that there's linear algebra also involved here, but also probability and statistics, and also elements of discrete math for doing graph analysis. In short, this course brings together a number of different areas of study from the program and applies it to this particular problem domain. The techniques and tools we use in this course are all open source, beginning with Hadoop. Hadoop is actually a combination of technologies, particularly a distributed file system and a mechanism for running MapReduce jobs. In addition, we'll be exploring streaming data analysis and processing, and that'll be using the Spark framework. These are both Apache projects and are open source. Finally, for the data analysis itself and also initiating jobs within these frameworks, we'll be using the R language. R is useful for exploratory data analysis and other forms of data science. By integrating it with Hadoop and Spark, we'll be able to perform our analysis directly from the R console while being able to operate on much larger data sets. So moving on to MapReduce. Map and reduce form the core of higher order functions in functional programming. They provide an abstraction around iterating over lists in particular ways. And we'll see that for the MapReduce framework, they've been repurposed for distributed computing. Because of the structure of these higher order functions, the underlying processing on each of the list elements can be distributed across multiple machines. Within the MapReduce framework, a number of algorithms have been restructured in order to be interoperable. And these include algorithms for linear algebra, including matrix multiplication and matrix factorization. We'll also see a number of ways to calculate relations over different sets and matrices. There are also set operations like joins, unions, intersections. We'll see a number of distance metrics calculated for use in similarity analysis, and then also functions and graph analysis that are distributed through MapReduce. It's important to remember that none of these algorithms are unique to MapReduce. What's unique about it is that these algorithms have been redesigned to be compatible with a MapReduce system that allows the algorithms to operate on much larger data sets. So in addition to the MapReduce framework and paradigm, we'll also be looking at streaming data. Batch processing ultimately works on discrete sets of data. Alternatively, we'll see that streaming data are more continuous in nature. And so there's always data coming in. This requires different ways of processing the data. Spark is a newer project that enables stream processing. For many, streaming data is a new way of thinking about data analysis and represents a brave new world. Some of the issues and challenges involved with streaming data, particularly for analysis and machine learning, are listed here. In particular, when you sample from data streams, the theory behind it is a little bit different from a static set, and so we'll be exploring this in the course. We'll also look at how to filter streams, how to count elements within the streams, issues related to creating windows around streams, and also counting and identifying frequent items within the streams, and then of course also repurposing or retooling some of the machine learning algorithms in order to operate on streaming data. We'll find that this is actually straightforward for a number of algorithms since they're iterative in nature, and so they can operate incrementally on the data as it comes in, and the learning will happen in lockstep. Speaking of machine learning, what are some of the methods that we'll cover in this course? We'll be looking at a number of approaches for dimensionality reduction, including PCA and SVD. We'll also look at various forms of neural networks, and we'll be looking at support vector machines and how those can run in parallel, and also various nearest neighbors. We'll also be looking at decision trees and random forests, which by their nature are easily parallelized and so can be extended rather simply to a big data context. To get started with this course, you'll need to have your environment set up properly. I've created a project on GitHub that provides basic installation of the tools necessary for the course. At a minimum, download the package, read the README file, and then make sure that you have a Java JDK and also a version of R installed locally. Then you can run from a bash shell the steps below, and that'll install Hadoop, it'll install Spark, and then also the components for R Hadoop. The libraries for R and Spark are actually built into the main library, so there's not anything special that needs to be done there. Do note that these instructions and the scripts provided will work primarily on Linux. They should work okay on Mac OS, but they definitely will not work on Windows unless you have Cygwin installed. So you may need to modify the scripts in order to get it set up properly. In short, this will be a fun class. I look forward to working with you all, and if you have questions about the setup of your environment, use the Ask Your Instructor forum on Blackboard or email me and I'll get back to you quickly. Thanks, and we'll see you soon.